welcome to the second one. As a lightning fast recap of the previous video, we talk about two types of supervised learning. We talk about regression, where we learn the relationship between a dependent variable and independent variables to predict numerical values. And we talk about classification, where we learn to predict the category to which new data belongs. In this video, I will talk about three supervised learning algorithms for classification: KNearest Neighbor, support vector machine, and Naïve Bayes. The first one is KNearest Neighbor, and this is a little bit different compared to the other models I will talk about. This is an example of lazy learning. In this model, there is no construction of a general prediction model that captures everything in the data that will then be used to make predictions. Instead, this method waits for as long as possible to do any work at all. The predictions in this model simply mimic the closest neighbors, and I will show with an example how that works. Suppose you now, for some reason, want to make a prediction of whether a new test suite will require more than 5 minutes to execute. And this is supervised learning, so we collect data here. Let our data be represented by two features. We have here on the x-axis the number of test cases in the test suites, and on the y-axis the lines of test code in the suite. And then we have some data here. So each point here is a test suite, and then let their average execution times be represented by the colors here. So red means it was a quick one, a short execution time, and the blue-greenish color here, these are the long execution times. And then you create your new test suite here and let it be this yellow data point here. And what you would do then with K-nearest neighbor classification would be simply to look at your closest neighbors. With a K of 1, you would just look at your closest neighbor and say, I'm probably like her. And in this case, you would say it's a red one, so it's a short execution time. And if you increase the K, you would then consider more of your neighbors and do a majority voting here. And this approach can actually also be simply used for regression by looking at the numbers, the actual average execution times of your closest neighbors, and calculating averages among these 1, 5, or 9 neighbors in this example. But k could of course be an arbitrary number here, but if k becomes a very large number, then it's just an average of your entire dataset in the end. When is this a good idea then? Well, it is an approach that brings you some explainability. The output is explainable here. It tends to work better if you have large datasets with few dimensions, but you might have to live with rather slow predictions. If there are many distance measures here to come up with between the different data points, it might take a while to reach the prediction. The next model I'm going to talk about is support vector machine, SVM. And this is a method, an algorithm with a nice geometrical representation. So what happens here is that you first span a room with your features, and then you populate this room with your data. And then you try to find a way, a hyperplane, to separate these two classes of data, in the case of binary classification, of course, but this can then be generalized to multi-class classification as well. Suppose now you want to make predictions for individual classes. You want to make predictions of whether or not they are fault-prone, and we've seen pretty much research in this topic. And we have some data here, and let our data be represented by, on the x-axis, the lines of code. of the class, and it's between 0 and 10,000 here, and on the y-axis we'll have the code churn normalized between 0 and 1. And code churn is often used to predict whether or not things are fault prone. And then we have some data. Let the green marks here on the bottom of the figure represent the not fault prone classes, and the fishy classes, the fish on top, these are the ones that have been classified as fault prone. So your first approach here could be to just look at the code churn and say, in this example, if it's greater than 0.5, then you would say that, well, the classes might very well be fault prone. But what you see here is that the margin between the separating line and the closest data point is very small. And if you have an example here of an additional class in this area, a new class you want to make a prediction for, you would then say that this is going to be a fault-prone class, possibly, and we should probably investigate it further. What you would do with SVM here is to instead try to find the best separating line when it comes to the margin between the classes here, and you would do that by iteratively updating your parameter weights here using stochastic gradient descent until you have reached the point where you have the maximum margin between your classes. And looking at the same example again, you would see here that your person now would actually end up among the not fault-prone classes, and this would then be a different prediction compared to just looking at the code churn in this example. So when is this a good classifier then? Well, it's very convenient if you have linearly separable classes, like in this example. It would be a bit more difficult if you had all the fishy classes in the center of this figure and then having the normal classes orbiting around it. But there are ways to deal with that as well. You would use a kernel trick here to map it to another representation and find a hyperplane in that space instead. But it is a method, SVM, that scales very well to many features. I've used it myself for text classification in the past, and text typically is represented by loads of features. Often each term, each word becomes a dimension in the hyperspace. But with SVM you might experience that actually training the model is a bit slow, but it is a good solid classification method. The final classification method I'm going to talk about in this video is Naïve Bayes, and this one doesn't have an as beautiful geometrical representation perhaps, but it is instead based on some very beautiful probability theory. Naïve Bayes, the name originates in a very strong assumption this method or family of methods actually makes. It builds on the very strong assumption of feature independence here. So it says that all features should be independent, and that's often not the case. But even if this is violated, this method might work fairly well, actually. I will show how it works with an example. Suppose now you are running tests in your test environment, in your test lab, and that the lab environment acts a bit flaky, and it doesn't feel totally deterministic whether or not your system tests will actually complete their execution here in this lab. So you want to make predictions for test executions while they are running of whether or not they will require some human intervention to actually complete. And suppose you start collecting data here now. In the first column you will see IDs of test runs on this lab environment. In the second column you will see a feature showing the time until you receive the first result from the test case you're currently running. And let the third column here be a binary variable, just saying whether or not the test that is currently run is testing a core feature of the product. And then the final column here is the label you want to predict here, whether or not there will be some human intervention required. And to make it a little bit easier here, in the example, and we will only look at the first 10 rows here in this table. Suppose you have you could perhaps have many thousand rows here in this table, but for to make it easier to discuss this, let's only consider the first 10. What you also could do here to make the example a bit easier is to do a very simple example of binning here in the second column. So instead of actually having numbers here for the test runs, we will only say that this feature here is either long or short. So the time until the first test result is either long or short. And what you see here in this table, looking at the first 10 rows, is that 40% of the test executions here required human intervention. So if we know nothing else, then the best guess would always be to say there will be no need for human intervention. 60% here required no intervention. The first thing you would do here when applying naive Bayes classification would be to collect your data from the previous table into frequency tables. This simply means summing up what you had there for each feature, for each value. So for the feature time until the first result, you will look at first the long execution times for getting the first result, and just look at how many were of these previous test runs required human interference. You found 3 of those and 2 did not require that, and then you would do it the same thing for your short executions, and then the same things for your core features. And what you can do then when you have this information is, I've already talked about the class probabilities actually, calculate some simple probabilities here. The probability of having an intervention here is 0.4, and the probability of having no intervention at all, we saw that before, it's 60%. What you also can do now, which is very easy thanks to the frequency tables, is looking at conditional probabilities. And in case you don't remember the notation, this is how it works. So what you see here is the probability of having a long test run to get the first result, given that there was an intervention. This means we now know there was an intervention. We know that we are looking at data in this part of our frequency table. Then if we know this, what would then be the probability that there was a long test run? And what you see here is that we have 3 long test runs and only 1 that was short. So 3 out of 4 here, it equals 0.75. And then we do the same thing for our other conditional probabilities here. We just calculate this using our frequency tables. And here comes the beautiful part. Here comes Bayes' theorem. So this old piece of probability theory, very beautiful theorem. So what we see here is that the probability of an hypothesis being true given some evidence is equal to what you see here on the right hand side, and I will walk you through what that means. So suppose now we have a new observation. We have new data and we want to make a prediction. We have now some evidence here. We have new data that we have a long test run. It took a long time before we got the first result from this test execution, and we are testing a core feature in this test case. And the question we ask now is the probability of having a human intervention now needed, given this evidence, is that greater than the probability of not requiring the human intervention given the same evidence? We're just interested in which of these probabilities is the greatest. And what we see first here is that the probability of the evidence itself being true, it is actually, it doesn't matter which of these hypotheses here we explore. The denominator here in Bayes' theorem on the right hand side, it will be the same, so we can consider this a constant and only look at the denominator here. So what we do in the denominator is we explore, we calculate, given what we see here on the left side, the probability of requiring an intervention, given that it's a long run of a core feature. It is equal to the probability of the intervention. So this is called the prior probability. Without knowing anything else, what is the prior probability? It's what we have here, 0.4. And this we multiply by the probability of having a long run, given that it was an intervention. And this is a conditional probability that we actually calculated over here. So we already have this, and we just take that number, and then we multiply that also with the probability of having a core feature here on the test, given that there was an intervention. And this is also a probability we have here. It happens to be the same probability here, 0.75. And then we just multiply these three numbers together and we get 0.225. And then we repeat the same process for the alternative hypothesis here, the probability of not having an intervention, given that it was a long run of a core feature, and we see that that's 0.065. And well, this value here is greater, and that means our prediction for this observation, the data we observed, is that this indeed will be a test run where human intervention will be needed. But as I said before, there is a strong assumption here, the reason why it's called naive Bayes, and that's that the runtime here to get this first test result is independent from whether core feature is under test or not. And this might be a strong assumption, this might very well be wrong, but it might anyway be possible to try this naive Bayes classification, because sometimes it works also when it's violated a little bit. So this is a classification approach that works well when you have limited memory available on really constrained devices. You can do this because it doesn't require to keep that much of an overall model in memory. It's only multiplying a bunch of probabilities together, and that's not a very expensive operation. Often if you have small data, this is good enough. When there isn't that much of patterns to find in the data, then naive Bayes can be sufficient for your predictions. This has been very popular for text classification, and the first generations of spam filters all were based on naive Bayes, and I think still it's an important component in spam filtering, but there are now many other features used and techniques used to do an even better job. Thank you.